Assalamualaikum and good day to everyone. In this video, I'll talk about steady-state error of a control system. When an input is applied to a system, the system will respond and this response will be divided into two parts. The first part is transient response and the second part is when the system is already at its steady state. During the transient response, we only would like to measure a few things such as how fast or how slow the system is responding, and also if the system is having overshoot or what is the peak overshoot the system is actually having. During the steady state, we only have one characteristic to be measured, which is the steady state error of the control system. So therefore, when an input is already applied to a system will undergo the transient response first. Then when it reach a steady state, this is when we have a steady state error. If the system is having steady state error, then we need to design a controller to actually overcome this steady state error. Before we can do that, let me just define you a closed loop and open loop system. Okay. Let's have a look at open loop system first. If I have an input applied to a system, let's say input of R, for a system that's having trans function of G and the output is Y, open loop system will give you an error of defined as error is equals to input given to the system minus output from the system. And at the same time, you know that output Y is equals to the input multiplied by the transfer function of the system G. We can substitute this relationship into our error equation so that our error is becoming R minus RG. At the same time, I can just factorize this, become 1 minus G multiplied by input R. So this is an error equation for open loop system. Okay, what if we have a closed loop system? Okay, so this is a closed loop system, right? If we consider a closed loop system like this, right, the system is now with a feedback, and the feedback is actually a negative feedback, and then you will have error is the comparison between the input and the feedback of the system. Okay, so if you look at the equation of closed loop here, okay, so the error is actually equivalent to error is equals to your input given to the system minus the Y multiplied by H. Okay, at the same time, you know Y is equals to E multiplied by G. Okay, so I can just substitute this value of Y into the first equation of error. So then my error will become E is equals to R minus EGH, okay, by substituting that value into your error equation for closed loop system. Okay, so then I can just collect the error together. I will have 1 plus EGH, so just 1 plus GH equals to R, and then I can write in terms of error alone. Error is equals to 1 over 1 plus GH multiplied by R. So this is the error equation for your closed loop system. Okay, so when we want to measure the steady state error, you need to actually identify if you are measuring open loop system or closed loop system. There's a lot of difference there. Okay. Next is when we want to measure system at system error at steady state, you must wait until the system reach its steady state. For example, let me just show you that. Let's say I have an input, a step input applied to a system. Okay, so what we want to do is actually check the response of the system. The system maybe is, let's say it is a second order system, it will respond like this. Second order will have overshoot and then maybe another sinusoidal effect there before it settle down. So then it will start to settle down. So this first part, before it settle down, this part is known as transient response. Okay, so that part will be your transient response. Where during the transient response, normally we would like to check if the system is having any overshoot, if it's fast or slow and whatnot. Okay, then when it start to settle down, so this is when you have steady state. Okay, during the steady state, you need to measure only one thing: is there any steady state error or not? Okay, then of course you need to do this when time is approaching infinity. You cannot do it in the beginning of the response. Okay, so you might want to wait until a while before it reaches steady state. So normally we will actually take the measurement when time is actually very big. Okay. So to do that, we need to have what we call final value theorem. Final value theorem is a measurement of your steady state error when the time is approaching infinity. So I will show you how to utilize a final value theorem in the next example. So final value theorem is just as simple as saying that to get your steady state error is by having limiting of your error in time domain when t is approaching infinity is equivalent by limiting your error in s domain when s is approaching 0. But in this case, you need to have not only s, you need to have es. Sorry, s multiplied by your es. Okay, so this is how you have a final value theorem for steady state error. Then the value e that you need to put here, the value e that you need to put here and here is depending on your open loop or closed loop system. Okay, so let's say I want to use this for open loop. How does it look like? And what if I want to use it for closed loop? How does it look like? Let's have a look at that. Right, so if I want to use open loop, I'll just apply the value of 1 minus g with input of r. Okay, in this case, let's say input r is 1 over s. So I'll put just 1 over s here. Okay, and then I need to limit s into 0. Then I will get my steady state error. Similarly, for closed loop system, okay, so for closed loop system, I can just put my e there, s multiplied by e there, that e there I will put 1 over 1 plus g h multiplied by input r. So in this case, input r, let's say it is a step input, so your equation will become like this. This s here and the other s there can be cancelled out, and then when you put your limiting s into 0, your system will have this kind of steady state error. Okay, to make that more visible, okay, more meaningful, let's look at an example to this. Okay, right, let's say we have a system with GH is equals to 1 over S plus 2. Okay, let's have a look at what happened to this system when it is open loop and closed loop. Okay, let's consider an open loop system first. So if the system is an open loop with input of r and the transfer function is s plus 2 and output of y. Okay, and let's have that transfer function, that input is a step input, okay, with a value of 1, r is equals to 1 over s. Let's apply that into our system. Okay, so according to our steady state error, using a final value theorem, steady state error is defined as limiting s into 0 of s multiplied by es. Okay, and that es here that we're going to use is when the system is open loop, the es is actually equals to 1 minus g multiplied by r, the way that we have defined earlier. Okay, so I'm going to substitute that value into my final value theorem, right? Okay, is equivalent to limiting s into 0 of s multiplied by 1 minus g, and in this case g is equivalent to 1 over 1 plus s plus 2. So 1 over s plus 2 multiplied by input, which is in this case a step input, 1 over s. Okay, and then we can straight away see that 1 over s from your input can be cancelled out from the s from the final value theorem. Okay, so we can do that, and then we're going to limit all the other s into 0 and check what is the response later on. Okay, so ESS is equivalent to 1 minus 1 over s plus 2 with all the s here equals to 0. So substitute s equals to 0 there. You're going to have half. 1 minus half, you're going to get 1, another half, isn't it? Another half is 0.5. This is really good. So not really, isn't it? The steady state error is really huge. So it means to say when you have an input, let's plot that, of a unity step input, okay, with a value of 1, when your system responding, it will give you 0.5 error. That is actually 50% error. So yes, it's really big. So the error that you're going to get is here, is steady state error is 0.5. So if the steady state error is 0.5, it means to say your response, your steady state output response is also 0.5 here, isn't it? Because 1 minus the error is all you have for your steady state output. This is really bad actually. For example, if I want to have a furnace with a temperature of 100 degrees Celsius, when I switch on the furnace without controller and nothing else, alright, when I switch on the furnace, the temperature will start to rise, and until one moment it start to settle down, and at that time the temperature is only reaching 50 degrees Celsius instead of 100 degrees Celsius. I want the temperature to be 100 degrees Celsius, but if we have this kind of steady state error, it means to say the temperature will only reach 50 degrees Celsius. Okay, there's a 50% error in the performance. So this is not really good. Okay, so normally for this kind of problem, we need to actually design a control to overcome the steady state error. All right, so let's say we want to design a control. Let's say we want to close loop the system first. So when we close loop the system, the steady state error is becoming different. Okay, it's not the same anymore, because the steady state error equation you have seen earlier, the error equation is not the same between open loop and closed loop system. Let's say I close the loop of the system like what we have in the slide just now. Okay, so let's say we close the loop, right? And then your system here is still the same system, 1 over s plus 2. Okay, but now instead of open loop, I'm going to close loop with a negative feedback, right? And that feedback h here, the value of h is equals to 1. I don't have any transfer function there, so it means to say the transfer function h is equals to 1 for the feedback. Okay, the input is still r, the output is y, and still I'm going to use a step input, okay, unity step input, so my r is 1 over s. I'm going to do that. I'm going to measure the steady state error. So according to steady state error, as steady state error just now, final value theorem just now, limiting s into 0 of s multiplied by es. However, that es that we're going to put there for closed loop is now, according to the previous derivation, is equals to 1 over 1 plus gh multiplied by r. So we're going to use this into that equation. Okay, so we're going to do that. All right, so we're not going to use the open loop equation, we're going to use the closed loop equation, because your system is now a closed loop system. All right, let's focus on that. Okay, so if I substitute the equation error into this final value theorem, I'm going to have s multiplied by 1 over 1 plus gh multiplied by r. Okay, so if I substitute the value of my gh, I'm going to have 1 over 1 plus, my g is 1 over s plus 2, my h is equals to 1. Okay, then I multiply with my input is 1 over s. Okay, so looking at that, we know straight away that input can be cancelled out with the equation from your final value theorem as that. Okay, so we cancel that out, and then we limit all the s inside your remaining equation and let it become 0. So I'm going to have 1 over 1 plus 1 over s plus 2, and with all the s in there becoming 0. So I have that becoming 0. So I'm going to have 1 over 2 plus 1, it's 3 over 2. 3 over 2, the reciprocal of it is 2 over 3. 2 over 3 is 0.666. Is it better? So we thought that when we close the loop, the system might give us a better response. But in this case, it's not really, isn't it? The error is becoming more, isn't it? So instead of having 0.5 when it was an open loop just now the error is even worse. It is, your response will be only 0.333 or 1 over 3, okay? Because why? Because your error is getting larger. Your error at steady state is now 0.666 instead of 0.5 when it was open loop system just now. From this exercise, you can see that closing the loop of your closed loop system doesn't necessarily improve the steady state error. In order for you to improve the steady state error, we can introduce a controller to the closed loop system. So if I add a controller, for example, a PID controller, GC in this case, and this controller is having only, for example, a P controller with certain value of your gain KP, and perhaps the gain KP can be added is maybe KP is equals to 2. Let's do that. Okay, let's do that. Let's add a KP equals to 2 as a controller to this system. So I still have the input of R, but now instead of having the transfer function straight away, I'm going to have a KP equals to 2 into the system. Okay, and then the system is still as before, 1 over S plus 2. Right? So now the feed-forward transfer function of this system has changes. It's no longer just 1 over S plus 2. It's now becoming 2 over S plus 2 because it's a combination between GC and the G of the controller. So the total G is equals to GC from your controller multiplied by GS from your system, isn't it? So that is becoming 2 over S plus 2. Okay? So from that, you can actually write your closed loop transfer function again. Sorry, not closed loop transfer function, but the steady state error again. ESS is equals to limited S into 0 of S multiplied by ES. But now your ES is having the controller GC into it. Okay, so what happened to that? So I have this, and I multiply my ES is again is a closed loop system, so the equation will be 1 over 1 plus GHS, so that G is now, instead of just GS, is now GC multiplied by GS multiplied by H, isn't it? Okay, so then that multiply with your input R. Okay, so let's have all the values being put into that equation. I have 1 over 1 plus, so we have 2 over S plus 2 multiplied by H. H is 1, so that's only leave it with that. Multiplied by 1 over S. Again, the input 1 over S can be cancelled out with this S from your final value theorem. Right? Then when we put the whole value of S equals to 0 into this equation, what we're going to have is that your ESS will be 1 plus with the 2 over S plus 2, and all that is becoming 0. So that S here is becoming 0. So you're going to have 2 over 2 is 1. 1 plus 1 is 2. 1 over 2 is 0.5. Okay. This is better than before, isn't it? This is much better than 0.666 error that you have when you close the loop without controller. Okay, so now by closing the loop, you have actually adding a control into it, you have actually improved a little bit of the error. Rather than having 0.666, you are now having an error of 0.5, again similar to your open loop, but now is having 0.5 error with closed loop. Let's plot that. Okay, so your input is initially is 1, right? Without the controller, if you remember just now when we plot, without the controller your error is 0.5. That was without controller or open loop system, isn't it? Okay, then when you close the loop without controller, okay, your error is becoming, this is a closed loop system without controller. Okay, without GC there. All right, so that is 0. You're having error of 0.666. Okay, then after a while when I add controller to it, your system has becoming closed loop system but with your error of 0.5. Okay, which is much improved than when you have your error is 0.666 in the beginning when you close the loop without controller. So by adding controller to the system, you are actually improving the steady state error of the system. What if I have more, the error, the controller is a gain with a higher value of gain? What if the controller is having a gain of Kp equals to 20 maybe instead of 10? So you can see that when Kp is equals to 20, what happens is that this value here is becoming 20. This value here becoming 20. Okay, and then this value here becoming 20. So when we have that, when S here is 0, so you have 20 over 2 is 10, 10 plus 1 is 11, 1 over 11 is really small, okay, it's 0.09, okay, 1 over 11. So when you have Kp is increasing the value from 2 to 20, what happens is that your steady state error will reduce, okay, so your steady state error just now will reduce, okay, from 1 over 2 into 1 over 11. So that is about 0.09. Okay, so yeah, when having the Kp, when you increase the gain Kp, yes, your system error will be better. It will improve your response much better. You're just going to have 0.09 error. But can we increase it more to improve the error? You can, however, there are some time when your Kp value, when you increase it certain value, it will affect the stability of the system. Sometimes for this particular problem, maybe it doesn't affect the stability of the system. You can increase your Kp into 1000 or higher than that. Okay, but there are some problem when you apply a higher value of Kp, it is actually affecting the stability of your system. From a stable system, it can turn to unstable system. So you need to take care of these two values. Okay, you need to actually play around with the value of Kp. However, at the same time, you must design your controller so that it is also fulfill the stability, the requirement of stability of your system. All right. So I think that is all for steady state error. So we can try with different values and different system for steady state error to check the stability of your to check the steady state error of your control system.